All right. Scalar equation. We're good?
Yes.
Okay.
It's there. It's there. I can see it.
Perfect. All right, so the scalar equation of a line in two space. Also called the Cartesian equation. Scalar equation is what we knew as standard form in grade 9 and 10. So it's this form, ax plus by plus c equals 0. Okay, and you're going to be looking at it in a whole new way after this morning. So we're learning to find the scalar equation of a line in two space in a variety of ways and learning to find the normal to a line in two space. So a vector perpendicular to a line is called a normal to the line. Okay, and normals are going to become very important. So starting off with kind of a grade 9 question, find a normal to the line y equals negative 2x plus 5. So we'll start off, I'm just going to do it on my whiteboard, and then we'll just do a little sketch here. But if I wanted to draw the line y equals negative 2x plus 5, I would know that the y-intercept was at 5. And the slope was negative 2 over 1 is the rise over the run. So I would go down to right 1 to get more points on my line. And then I'd be able to draw on my line. So one thing I really wanted everyone to get yesterday was the difference between a vector and a line. So a line goes on in both directions forever, whereas a vector has a starting point and an end point. Okay, so it starts somewhere and then the arrow only goes in one direction. And a normal to a line, we could have it starting anywhere, but it's direction that's important. It has to be perpendicular to this line. So if we know that the slope of this line, so back to grade 9 notation, the slope of this line is negative 2 over 1. What would be the slope of a normal to the line? Anyone?
1 over 2.
Yes. So negative reciprocal. Very good. So a normal, oops, that's not a good color to use. A normal is the negative reciprocal. So its slope that would be perpendicular would be 1 over 2. And I could start anywhere. Like I can start here if I want to. And that would mean I would rise up 1 and go over 2. And then it's a vector. So my starting point could be here and my ending point could be here. My vector can be as long as I want it to be or as short as I want it to be. But this vector is considered to be a normal to the line. Okay, but so that there's the idea in a picture. Now let's write it out on our lesson here. So if we know the slope of the line, you learned this yesterday, is negative 2 over 1, and we know slope is change in y over change in x way back from grade 9. We can change the slope to a vector, a direction vector. So we instead say that the direction of the line is from 0, 0 to 1, negative 2. That vector from 0, 0 to 1, negative 2 would represent the direction of the line. Is everybody good with that from yesterday? Direction of line. And the letter we use for the normal vector is an n, which makes sense with a vector over top. So a normal to the line would be a vector that starts at 0, 0, an algebraic vector that starts at 0, 0 and goes to 2, 1. So let's make sure that that's right. And look what I did. I flipped the x and y components and changed the sign. So if one's negative, they're both positive. If they're both positive, one would be negative for the normal. That's analogous to the negative reciprocal. So if I were to draw the algebraic vector 2, 1, it would start at 0, 0 and end at 2, 1. And you can see that that's the same direction as the normal we drew to the line. It's got the exact same direction. Yep.
If your m is both positive, which number in n would be the negative one? Does it matter?
So here, oh, I see what you're saying. Yeah. Okay. So you're saying, what if the direction instead was 1, 2 for our direction vector? What would our normal be? Is that what you're saying, Hannah?
Yeah.
Okay. So by convention, textbooks always put the negative on the second number, but it doesn't matter is the answer. So you could have had -2, 1 as well.
Okay, thank you.
Does that make sense? But if you're looking for a textbook answer, they always put the negative with the second. But it doesn't. You'll see why when we're finding the scalar equation of a line, but it really doesn't matter. Just saves you a step in algebra. Okay, so that's the idea then of a normal. And remember, a normal, we already defined it, so I won't write it out again, but a normal is a vector perpendicular to a line. Okay, so question 2 says find all normals to the line r equals 2, -3. So we think of that as a point we know on the line, plus our parameter t times the direction vector 2, 5. So in this case, we are reading that line and saying it's got a direction of 2, 5. So what would a normal be? Let's not worry about all normals right now, but what would a normal to that line be?
Could be 5, -2.
Yeah, 5, -2. So that's a normal. All right. And then Hannah kind of already said this as well. We could have also had -5, 2. Okay. But really, in actuality, any scalar multiple, so any number times 5, -2 is going to be a normal. So we can say all normals would have the form some constant k times the vector 5, -2. That would be all normals to the line. And they would all have the exact same direction. Okay, just keep that in mind. This gives you the length, or helps you determine the length of the specific normal you're drawing, but doesn't change the direction at all. And that's like a little definition here. All the normals of a line in 2 space can be written as k times n. For this reason, we consider lines in 2 space to have a unique normal because they all have the same direction. And that's really super important because this afternoon, you're going to start learning about lines in 3 space. And if I can just kind of make my pencil on an angle representing a line here, if you think about a line in 3 space having a normal, well, this direction is 90 degrees to it. This direction's 90 degrees to it. I can go all the way around and be 90 degrees to it. Do you guys see that? And if I go into 3 space, so there's an infinite number of directions, different directions that are normal to a line in 3 space. So in 3 space, there is not a normal to a line. Because there's not a unique one, we just say that we don't have a normal to a line in 3 space. Because there's too many possibilities. There's an infinite number of possibilities, whereas every normal in 2 space is a multiple of the same direction, okay? Not an infinite number of different directions. All right, so keep that in mind for this afternoon's lesson. So find the equation of the straight line that passes through the point Q, -2, 1, whose normal is n, 5, 2. So, and I should say scalar equation here. I forgot that. So meaning we want ax plus by plus c equals 0. All right, so we know it goes through this point, -2, 1, so I'm going to plot it. So here's Q. How does knowing its normal is 5, 2 help me draw the line, first of all?
We could have the negative reciprocal for
Our direction, nice,
direction.
okay. So if we know a normal direction to it is 5, 2, then we know the direction of the line must be 2, -5. They're negative reciprocals again, right? That's how they're related. So if we know that this is the direction of the line, then from our point Q, we can go over 2 and down 5. Because remember, this is a direction from 0, 0 to xy. So we want to be parallel to that direction. So I'm just going to sketch our line in, and I'm going to propose something to you, and you guys can agree with me here. So this is like an easy way to get the scalar equation of a line once we know that this is true. So this is our point Q, and we also know the normal to the line is 5, 2. Okay, so I'm going to go from point Q and use 5, 2 as my normal, which means from here I'm going to go 1, 2, 3, 4, 5, and up 2, and this should be a normal to the line. I'll draw that in a color, just to be nice here. So this vector I've drawn is the normal, 5, 2. This point on the line I know is -2, 1. And I'm also going to pick a point P on the line that I don't know and call it X, Y. And I'm going to create a vector between Q and P. So Q is going to be the tail of the vector, and P is going to be the tip. So that vector lies along the line. And because the vector n, 5, 2 is normal to the line, the angle between them is 90 degrees. So what I want to propose to you is that the vector QP, point-to-point vector QP, dotted with the normal n, is going to equal 0. And do you guys agree that would be a true statement?
Yeah.
So if I dot product vector QP and the normal, because they're perpendicular to each other, I have to get 0. So vector QP then. So let's find vector QP. We know it's P minus Q. So vector QP is going to be, so P is our x coordinate of P is x. X minus -2 is x plus 2. Y minus 1 is y minus 1. So vector QP is x plus 2, y minus 1. So I'm going to replace vector QP with vector x plus 2, y minus 1. And we're going to dot that with our normal, 5, 2. And we know that that has to be 0. And we also know that how you dot is multiply and add. So if I'm multiplying x plus 2 by 5, I'm really multiplying the x by 5 and the 2 by 5. So x plus 2 times 5 gives me 5x plus 10. And similarly, if I'm multiplying y minus 1 by 2, I'm multiplying the y by 2 and the -1 by 2. So that's going to be plus 2y minus 2 equals 0. And then the only like terms are the positive 10 and the -2. And I can collect them and get 5x plus 2y plus 8 equals 0. And that is the scalar equation of the line. But if we want to be convinced, how could we show this another way, that this is the scalar equation of the line? What did you learn yesterday, a way of getting the scalar equation?
I guess getting it from the symmetrical.
Right, getting it from the symmetric. So if we know that a point on our line is -2, 1, and we know the direction, so I'll start off with a vector equation of the line, which would be r is -2, 1 plus t times 2, -5. And so if I want symmetric equations, I might get the parametric first. I'm going to run out of room here, but I want to write it down so that you're convinced. And then we're going to use this first way going forward, but I want you to believe in it. So there's my parametric. To get symmetric, then I want to pretend to solve for t in each of these. So to get t by itself in the first one, it's going to be x plus 2 over 2. And to get t by itself in the second, it's going to be y minus 1 over negative 5. And then to get scalar or standard form, we used to call it from that, you would multiply both sides by the common denominator, which is 10. So 10 divided by 2 is 5. 10 divided by negative 5 is negative 2. Distribute. Get everything to one side. So you do get 5x plus 2y plus 8 equals 0. Okay, so that's the other way that we learned yesterday to do it, but we're going to use this way to do it because it's quick and easy. All right, everybody convinced that we can use this way to find the scalar equation of a line? Hopefully, we'll get there. All right.
All you need is a point and a vector.
Yes, all you need is the normal or the direction vector and a point, exactly. Pretty cool. And, okay, oh wait, sorry, I forgot to show you something else cool too. Notice the coefficients of x and y are 5 and 2. And what's our normal? 5, 2.
Whoa.
Not a coincidence. I know. Remember how in grade 9 you weren't kind of sure about how great that equation of a line was, like what the A and B meant? Now you know. Okay, so the scalar Cartesian equation of a straight line in a two-dimensional plane has that form, ax plus by plus c equals 0, where the normal is AB. So if you're looking at the equation of a line in standard form or scalar form, then you can tell what the normal is just by looking at it. And this is our setup that we're always going to have. And then we're always going to calculate our scalar equation by saying QP, the vector QP, so the vector from here to here, dotted with the normal, is equal to 0. And they form a right angle because normal is perpendicular to the line. And there's our setup. Okay. So our next question says, find the scalar equation of a straight line passing through the point -3, -7 if the normal to the line is n equals 3, -2. So this is my basis here. So I need to know Q, which is a point on the line that I know. And that in our case is going to be -3, -7. The point P is another point on the line, but an unknown point, x, y. And N is the normal to the line. And those are the three things I need to know. Check, check, check. And then I can make my equation. Vector QP dotted with vector N, the normal, is equal to 0. So to make vector QP, it's P minus Q. So X subtract -3. That's the only place maybe you could make a mistake, but when you subtract a negative, you add. Y subtract -7 is Y plus 7. Dotted with the normal, 3, -2 equals 0. Dot product is multiply and add, and remember you need to distribute here. So x plus 3 multiplied by 3 is actually 3x plus 9. Y plus 7 multiplied by -2 is actually -2y minus 14 equals 0. And then collect any like terms. and you have your scalar equation. Just one thing I forgot to say, which is important, because this comes back to Hannah's question. A always has to be a positive whole number. And that's why when you're making a normal, if one of the components has to be negative, you usually put it with the y value. So just make sure when you're rearranging it, no matter what you end up having your normal be, but when you actually rearrange your final answer, the number in front of x should be a positive whole number to actually be in scalar form or Cartesian form. All right, question 5. Find the scalar equation, of this line, and this line's in vector form. So right now it's in vector form, but I want to find it in scalar form. So again, I need Q, which is a point I know on the line. Anyone know a point on this line based on its vector equation?
1, -5.
Awesome. P is a point I don't know on the line. We call x, y. And this 3, -5 is not the normal, it's the direction vector. So if I know the direction vector, then does anyone know what the normal would be?
Negative reciprocal.
Which is?
Would be -3, 5.
Nope. 3, -5. So you want to switch the numerical parts of the components.
Oh.
And then change the sign, right? So you want, if one of them's negative, they're both positive. If they're both positive originally, one's going to be negative. That's how negative reciprocal works in vectors. And then you want the components to switch spots too. Okay, so now that you've got QP and N, it's easy. That's the hardest part, really. So now you just make vector QP, dot it with N, set it equal to 0, and your scalar equation will fall out of that. So vector QP is P minus Q, so X minus 1, Y minus -5, which is Y plus 5, dotted with the normal to the line. Dot is multiply and add. So X minus 1 times 5 is 5X minus 5. Be careful that you distribute. Y plus 5 times 3 is positive 3Y plus 15. And then collect these like terms. So your scalar equation is going to be 5X plus 3Y plus 10 equals 0. And you should always do like a little check at the end and make sure that your normal and your A and B line up with each other. Also remember A has to be a positive whole number. Okay. So question 6, find the scalar equation of the line, and now the line's given to you in parametric form. So who can tell me a point on this line based on its parametric equations?
Would 1 point be 0, 5?
Yes. Okay, so some people can just look at that and say, okay, I know it's the non-t parts. Okay, so 0 minus 3t if there's no number there, and 5. Other people, I used to do this when I was in high school. I'd always change it to vector form first. So I really am thinking the point would be 0, 5. But for some reason, it just helped me to write out the vector form. And you'll fall into one of those categories. It doesn't matter. We're just learning. Our point P we don't know is going to always be x, y. Now we want to get the normal. So here's our direction vector. So we have to recognize how to get the direction vector, and maybe rewriting it in vector form will help you with that. So if our direction vector is negative 3, 2. What's a normal to that direction?
I'll give it a second shot. This would be 2, 3.
Yes, very good. 2, 3. Okay, so now you've got your QP and N. So now you just make vector QP, dot it with the normal. It equals 0. So P minus Q is going to be X minus 0. So you can just write that as X if you want. Y minus 5. Dotted with our normal 2, 3 equals 0. Multiply and add. So 2x. And then distribute here. So plus 3y minus 15 equals 0. And there was nothing to collect. So that's just our scalar form of our equation. And we can see that a, b is 2, 3, which is our normal. All right, next question. Find the scalar equation of the line through the point 6, 3. So as soon as I see that, I'm thinking, okay, Q 6, 3. Parallel. And yesterday in the video, I talked a lot about parallel in lines, especially meaning same direction as. Parallel meaning same direction as this line. Okay, so here's the line. We have to know that same direction means same direction vector as, or same parallel. Parallel means same direction vector as. So we know that the direction of the line we're talking about is going to be the same as this one, which means the normal would also be the same. So in two space, we've got parallel, same directions, also means same normal. So the normal of this line would be 2, 1. And once you've set that all up, you're ready to go. With vector QP dotted with N equals 0. Multiply and add. So 2x minus 12 plus y minus 3 equals 0. So 2x plus y minus 15 equals 0 would be our scalar equation. All right, the next one's a bit of a thinker. Find the scalar equation of the line passing through this point. So we've got our Q. We always know P is XY. So find the scalar equation of the line through the point 511 perpendicular. So that's not going to be same direction as, perpendicular to this line. Ideas, and the line's given in scalar form.
I guess we need the vector or direction of that line in scalar form. I guess we could use the slope that you can get from the first two coefficients.
Okay, so you guys are good. If we're just talking about the line 2x minus 7y plus 12, we know the normal to this line here is 2, negative 7. Is everybody good with that?
Yeah.
Yes? Okay. So what's the direction vector of this line here highlighted? If its normal is 2, negative 7, what's its direction?
7, 2.
Good. 7, 2. Now we want to be perpendicular. We want our line to be perpendicular to this line. So what's the direction of our line? So this all has to do with this line here. So our line has direction. I'll call it M2. What's the direction of our line? It's perpendicular to this direction. Does everyone agree? It's perpendicular to this line. Okay, so it's perpendicular to this direction, so it's 2, -7. So what's the normal of the line we're trying to find?
7.2.
Yes. Now, some people can just go straight to that, and that's fine if that's you, okay? If that just clicks in your brain. But I had to write out, okay, I know the normal of this line, so I know its direction. I want to be perpendicular to this line, so the direction of the line is 2, -7. But to get the scalar equation, I need the normal, which is 7.2. So that was my thinking. So once I've got that, I can just go back to QP dot n equals 0. So QP is going to be x minus 5, y minus 11, dotted with our normal. And now it's the easy part. So multiply and add 7x minus 35 plus 2y minus 22 equals 0. So that's going to be minus 57. 7x plus 2y minus 57 equals 0. Okay, and that's probably kind of like the hardest scalar equation question you would get. We've done taking it from the vector equation of a line, from parametrics, from just given a point and a normal, all the different ways. So I think now we're going to move on to shortest distance, which is a cool application of scalar equation of a line. So this is where you need your ruler. So the shortest distance from a point to a line will always be along a normal from the line to the point. It will be perpendicular. So consider this problem. Find the shortest distance from the point P55. So I'm going to plot this point here. To this line, 5x minus 7y minus 10 equals 0. Okay, so we need a easy-ish way to draw this line. So I always look for a point in a direction, okay, when I'm drawing a line. And the points I always look for that I hope are one of the two is going to work is either it's easy to find the x-intercept and plot it, or it's easy to find the y-intercept and plot it. Can anyone look at this line and tell me what's easier to plot on my graph, the x-intercept or the y-intercept, and kind of explain why? Okay.
The x
No one's gonna-
because
yeah.
5x minus 10 equals 0 is just x equals -2.
Good. Okay, so when you're looking for the x-intercept or the y-intercept, you know, for x-intercept, you set y equal to 0 and solve for x. To find the y-intercept, you set x equal to 0 and solve for y. So one of those two things. So I can see that if I ignore that term there, 5 goes into 10. So I know it's going to be nice. Whereas if I ignore this term here, 7 doesn't go into 10 nicely. Okay, so I know it's the x-intercept is the one I want to find. So if I find the x-intercept, I set y equal to 0 in this equation and solve for x. So I would add 10 to both sides and divide both sides by 5. So I get that the x-intercept is 2, and that translates to the point 2, 0. So just make sure you know which one you found so that you plot it in the right spot. So 2, 0 is here, because we're used to always plotting the y-intercept. So I find when you change it to the x-intercept, your instinct is to plot it here, but it's here, okay? Now we just learned today that we know the normal to this line is 5, -7. but we also, because we know the normal, can get the direction of the line. So if we know the normal's 5, -7, what's the direction?
7, 5.
Yeah. So once we know a point on our line, this point right here, and a direction, we can find more points on the line. So from this point, I can go over 7, 1, 2, 3, 4, 5, 6, 7, and up 5, 1, 2, 3, 4, 5. And I kind of fell off the page there. I'll see if I can reverse it. 1, 2, 3, 4, 5, 6, 7, and down 5. And then I can take my ruler and draw this line here. So you don't need to draw the line and the point in order to find the distance. We will be making a formula that you can always use, but when you do need to do it, remember, try to look for the X or Y intercept, and you'll need to do that anyways when you're finding your point that's on the line, your known point on the line. Okay, so we've set it up where we've drawn our line and our point, and we want to find the shortest distance between this point here and this line here. And we said it's going to be along the normal direction. So from my point, the normal direction is 5, -7. So I'm going to go 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6, 7. And I'm going to just draw in a normal here. So there's my normal, 5, -7. This is my point, 5, 5. And I'm going to call this point that I know on my line Q. I'm going to stick to calling known points on my lines Q, and it's 2, 0. And do you guys agree that it's this, actually I'll use a marker. It's this distance right here that's going to be the shortest distance from the point to the line, what I just drew in orange? That's going to be D, my shortest distance from the point to the line. Oh, can you really see that in orange? Yeah. Does everyone agree with that? It's going to be my shortest distance there because it's perpendicular to the line or along the normal to the line. Okay, so this is how we're going to do it. It's kind of cool. Everyone's favorite thing is projections, I think, right? So I'm going to make this vector Q to P. So I'm making the vector Q to P. And the light source is coming in perpendicular to the normal. So here's my light source. So if I'm projecting vector QP onto this normal here, so I'll make my, this is my normal. And I'm projecting this vector here, QP. This vector onto this green normal here. And here's my light source perpendicular to the normal. So this vector projected onto the normal is going to be that orange distance D that I want. So the shortest distance, this distance D here, is going to be the magnitude of the projection of vector QP onto the normal, which is pretty cool. So the magnitude of the projection of vector QP onto the normal is going to be our shortest distance. So we know all that stuff that we need. We also know that the magnitude of a projection, we know a formula for that. So the magnitude of the projection of QP onto the normal is going to be the magnitude of QP dotted with N over the magnitude of N, because that's how the formula for the magnitude of a projection works. The little guy does all the work. And this is a distance one, so our answer is a number, not a vector. So we know Q is 2, 0 and P is 5, 5. So we can find vector QP by just doing P minus Q. So 5 minus 2 is 3. And 5 minus 0 is 5. Dot that with the normal. which is 7, 5, which is 5, -7. And it's right off the screen now, but it's 5, -7 is the normal over the magnitude of the normal. So the square root of 5 squared plus 7 squared. Dot product is multiply and add. So I'm going to do the absolute value of 15 minus 35 over the square root of, it's going to be 49 plus 25 there, which is 74. Well, I'm glad this came out negative because that was something people were getting wrong there. So 15 minus 35 is -20. But the magnitude of -20 or the absolute value of -20 is +20. So it's 20 over square root of 74. And let's get it approximately because we have a picture here to go with it. So 20 divided by the square root of 74 is approximately 2.3 grid units here, which makes sense if you look at it. So this orange distance here is about 2.3 grid units long. So that's the shortest distance from the point P55 to the line 5x minus 7y minus 10 equals 0. And this is your important formula. This is also your important formula. And you need to know Q, which is a point on the line you know, the point you're finding the distance from, and the normal to the line. Those are the 3 things you need to know. All right, so in our next question, we're going to find the distance first, just using our formula, and then we're going to draw it and see if it makes sense, okay? So find the shortest distance from the point P16 to the line 3x minus 4y plus 8 equals 0. So we're going to start off with our formula that the shortest distance is the magnitude of the projection of QP onto the normal. So then what things do we need to know then? We need to know Q, which is a known point on the line. So here's my line. Is it easier to find the x-intercept of this line or the y-intercept of the line?
Y-intercept.
Everyone good with that? 4 goes into 8, 3 doesn't. So we're going to find the y-intercept of the line, which is going to be our Q. So I'm going to do that here. So my y-intercept is when I set x equal to 0 for the line. It's going to give me -4y plus 8 equals 0. Subtract 8 on both sides. And that's going to give me y is +2. So it is on the y this time. But what you really need to know is that represents your point Q, and it's the point 0, 2, not 2, 0. Okay, so there's your point Q. Here's my point P, so I'm going to highlight this. There's P right here. That's the point I'm trying to find the shortest distance from. This is my known point on the line. And what's the normal to the line?
3, -4.
Yeah, 3, -4, the coefficients of x and y. So those are the 3 things I need that are in this formula. So I've got everything I need. So without even drawing it, I can find the distance and then we'll draw it just to make sure a distance makes sense. So we know that that's going to be the magnitude of vector QP dotted with vector n over the magnitude of vector n. So QP then is P minus Q. So it's going to be 1 minus 0, which is 1. 6 minus 2, which is 4, dotted with the normal, 3, -4, over the magnitude of 3 squared plus 4 squared. So the magnitude, dot product is multiply and add. So the magnitude of 3 minus 16 over, that's the square root of 25. That's nice. So the magnitude of negative 13 over 5. So the distance is positive 13 over 5 units. And we can figure that out as a decimal. So we can, when we look at our picture, it makes sense to us. It's 2.6 exactly units. Okay, so now let's draw it in and make sure it looks right. So here's our point 1,6. 1, 2, 3, 4, 5, 6. This is our point that we're trying to find the shortest distance from. This Q is our known point on the line. And this line, since it has a normal of 3, -4, this line's going to have a direction M of, anyone? If we know the normal is 3, -4, what's the direction of the line?
It would be 4, 3.
Yes, good. 4, 3. So from Q, we're going to go 1, 2, 3 over 4 and up 3. Over 1, 2, 3, 4, up 3. 1, 2, 3, 4, down 3. So we've drawn our line in. And we know that the shortest distance from point P to the line is going to be along the normal 3, -4. So from my point, I'm going to draw in 3, -4. So 1, 2, 3, 1, 2, 3, 4 is here. This is the normal. N. And we know the distance we want is going to be this distance here. And does that look like 2.6 units-ish? Yes. So we're right. Any questions? I think that's the last question. So the questions, you won't always have a graph. You don't need to do a graph, but you can check on Desmos. You could easily draw your line on Desmos and compare it to the point and see if your answer makes sense. All right,
So,
awesome. Yeah?
So if you were in 3 space,
Yeah.
you couldn't find the normal to a line, but you could probably find the normal to a plane.
I know
Right.
you can, but you can, yes. So this afternoon, you're going to learn how to find the distance from a point to a line in 3 space. And obviously, it's not going to involve a normal because in 3 space, there is not a unique normal. So you're going to see a different way, which is kind of cool. Okay. And then next time I have you, next week, we'll find the shortest distance from a point to a plane. Okay. Because
Cool.
the last week you have me, we're going to focus on planes mostly. Monday's going to be intersection of lines, but after that, the rest of the week will be on planes, okay?
So I guess we'll get to go flying around and
That would be fun.
yeah,
Yes.
test out some planes.
Yes. All right, guys, I'll stop recording. Go back to our screen here.